Alrighty, hello, welcome. We are here today to talk about design patterns and practices for distributed systems. Just a little housekeeping, so welcome. We do run a subscribers only chat. You need to be subscribed for at least 5 minutes before you can chat, so please join our channel if you want to chat with us during the presentation. I do watch the chat as I am giving this presentation, so rest assured, if you have a question, please post in chat and I'll do what I can to answer it. If it's not something I can address now, I'll let you know and we can address it later as well. Let me see, we've got that. This is subscribers only, so let's jump into this. All right. So we're going to be, again, talking about patterns and practices for distributed systems. This is a very focused thing. Now, we have a lot of information to cover in a short period of time. And with these being more complex problems, I don't want to try to rush the code. It's not worth it to rush through the code. So there's a lot to cover, a lot of suggestions, a lot of how do we get through this. There are some code samples at the end, but they are toward the end. So just so you're aware, I know some of you are like, where's the code? It's coming, but it's at the end. We are currently working on some courses regarding some of these patterns as well, and those will have a lot of the code as well. So, all right. Distributed systems are challenging. They aren't straightforward. They're not simple CRUD apps. We're talking these are over multiple systems, over the cloud with multiple regions. There's various things that can happen here. So we're talking about problems like reliable communication. We want to make sure that everything is working like it should. We've got fault tolerance. So if something fails, is it going to impact other services? We got to keep an eye out for that. Talk about problems with things like load balancing and how do we manage the load and how do we scale, and some scalability as well. Distributed data consistency and more. So these are the types of problems you're going to see in distributed systems. They're not an easy, oh yeah, this is just a simple design pattern, golden hammer, let's use it everywhere kind of deal. That's not how any of this works. The patterns and practices I'm going to show today will make more sense as we look at them. I'm going to take you through a bunch of different scenarios, point out the problems, and then talk about some of the ways we can solve it. So the first one I want to show is what we call the shopping cart snafu. Now, this particular product, the cup of tea, is one of our products shown in our eShop on Web sample. So let's say that we've got a cup of tea on sale and everybody wants it. We only have maybe a couple things in stock, so very limited inventory. How do we manage it so that the people get it, and then the people who can't get it get notified appropriately? There are different patterns and practices we can implement here. But think about it this way. Without the proper distribution management, many people could easily check it out and then fight over it. And that gets to be either you're overselling or you're getting out of stock and they've already charged, so now you gotta deal with refunds. You don't want to be in that spot. So what we can take a look at this. So consistency and transactions are the problems. What we want to do is we want a smooth user experience here. We want to maintain our data consistency under high concurrency. We want to make sure that if we've got that flash sale and everybody has to have this, the ones who are able to get it, and those who aren't let down completely horribly with a bad experience. So one of the things we can do is optimistic locking. When you go to check out an item from a cart, or when you go to check out an item, you'll check then to see whether it's available. So what happens is you add the item to your cart. Instead of having a lockup, okay, you are guaranteed this item, you have what is basically a lock of, okay, we're going to check the version of the item right now. We'll put that in your cart. When you go to check out, then we're going to check that version versus what you have in your cart to see, did they change? If they didn't change, then you can move forward. But if they change, now you have to take a look at the new version and see, okay, how does this work? With optimistic locking, you can do the inventory has changed, please review your cart. We see this with various e-commerce sites or shopping websites where you're going online and you're like, you know what? I need to get another pack of paper towels, for example. What do you mean they're out? Oh, it's no longer available from that supplier. So those kind of situations, that's what we're talking about here. Or that inventory might be there, or it might not because other people may get it in the process. So this is optimistic blocking. I'm going to grab my laser pointer here so you can see it. So we've got two people, user A, user B. They both get the same version of the item. The inventory service is like, okay, we've got a success here because we've already had somebody who fetched it and updated it. User B is like, I want to update it, and when they go to update it, this is where that check will happen and go, okay, your version doesn't match the version we have here, now we need to revisit it. So that's optimistic locking and how that gets implemented. All right. Next, I'll talk about request queues. So with request queues, so this is, again, talking about that problem of you have multiple users going after a limited supply, and how do you handle this? Request queues are an option. So basically what happens is when they're adding an item to the cart or they're checking out, that request will go into a queue for processing. So it gets processed sequentially. What's nice with this kind of setup is you can say the whole, please wait while we process your request. The downfall to that is the please wait. Users sometimes aren't good about waiting. They'll refresh it and cause more problems, or they'll just go away. And you don't want either one of those. Now with request queues, so you got to be careful with how you manage the queue size. The other thing is managing the resources. So something like a flash sale, something with sales around the holiday times, for example, high demand and limited supply, you want to make sure that you can keep up with that. So again, looking at our request queue, we've got two people who are adding to cart, and then inventory processor is going to process the queue. And with the queue, it's going to go, okay, this one was first in, first out, and continue on. So that is another option for handling the situation of multiple people, limited inventory, and how do you handle that? User experience-wise, request queues can be good, but it's not as good as saying, you know what, check your cart again. Because again, please wait can take a little bit, possibly. Now another option is rate limiting. So you want to limit the number of requests for a duration for a user. This goes back to the whole, sometimes you have users who are impatient. How many of us have gone to a website and mashed F5? Refresh, refresh, refresh. So, I mean, that happens. And when that happens, then it's one where we have to make sure that we account for that. Well, rate limiting, we could say, hey, you know what? You've hit this endpoint too quickly. And take it from there. So the user experience behind that, I mean, when you're returning your too many requests, that could be as simple as HTTP status 429, which I've seen on many servers. But then that's a developer standpoint, that's how we see things. We then can translate that to something on the front end for our users to actually be patient and wait, and don't mash F5 in a way that would make sense for them. And again, this is to do the preventing of rapid adding and removing. So think of it as people who are like, you know, this is that hot console of the season. I need a new console for my games. Let me get it right away. Oh, but it all got snatched up by bots. Let's prevent that. Again, rate limiting can help with that. Think of it as too many requests. Please try again later. And you just have to be careful with that in terms of making sure that it's fair for your users. So when you're looking at implementing something like rate limiting, you have to think of, okay, how many requests can I allow from a user and which duration of time? It's an art form because you have to figure out like what makes sense in terms of slowing things down so that your servers can handle it, your resources can handle it, versus making sure that you get the sale as well. So rate limiting is an approach. Another approach is reservation with expiration. We see this whether you're getting, I like to put it in context of maybe you're getting movie tickets or concert tickets, or in this case, conference tickets. Star Trek's happening next week, week after, it's coming up. But notice that we have a countdown timer. So it's very clear that you're going to be able to get this ticket as long as you finish this process within this countdown timer. countdown timer is animated, it is very clear that you have this throughout the entire process. So when you register, when you put in your name, when you deal with all the other details they need, things like that. Reservation with expiration means that you're taking account of inventory temporarily, so you're reducing the inventory, but when the timer expires, then it gets released back into the inventory. So that's how reservation with expiration works. Again, common scenes that I've seen are like movie tickets or anything that needs a reservation, really. But when you're making these kind of decisions, you want to make sure you implement it with a good user experience that is clear. Okay, you have a limited period of time. Now, something like 40 minutes for this makes sense because there's a lot of questions to answer. If it's a shorter process of here's your payment information, and then just give me what I'm paying for, then you might not have as big of a timer. Understanding the process and how long it takes will help you to figure out how long to limit that as well. And the thing you have to keep in mind when you're implementing something like reservation with expiration is that you need to track and expire those reservations. So if I'm sitting there at the checkout and I get distracted and totally forget it, and now the time is expired, I, as a user, should be able to see that it's expired. Now I'm going to have to go through it again. Thinking more about our flash sale, another approach is pre-computation and pre-allocation. So you may have your environment distributed to a point where you can say, I have multiple shards serving my site, and each shard might be allocated a certain amount. Now, shards, they could be geolocated. So you might be like, we have this event that's on the West Coast. Let's put a higher priority to the locals. And so that shard happens to be allocated a higher amount. Now, the trick with pre-allocation or pre-computation is that it's a set number of items, and usually it's split across shards or multiple servers. But you want to make sure you have accurate forecasting for it. And you want to make sure that you're tracking both the pre-allocated inventory. So what we have in this particular scenario is that we have 3 different shards, 100 total tickets, and then in those 100 total tickets, so here's my total stock. But I still need to keep track of, okay, shard A, somebody purchased a ticket, so that's 29. Then recalculate our total stock. So keeping track of all those numbers, you just need to make sure you track those well. Now, you're going to see that you can combine some of these patterns, and then if that's what makes sense for your situation, then do it. So optimistic locking, you want to use it for concurrent updates and making sure you're maintaining your actual inventory count. You want to do a request queue sometimes when you're dealing with checkouts in a controlled manner. Again, it's sequentially because it is a queue. And then you want to make sure maybe something like inventory, like a reservation with expiration makes sense for your environment. Again, anything with reservations. So if you're going out somewhere and you need access to it, then you do that. And then if you're worried about your system getting abused, consider implementing the rate limiting pattern. Now, rate limiting and a few of these other patterns will have a recommendation at the end as to which library to use. In .NET, one of the packages we use is called Poly, so we'll show a little bit of that. Now, some user experience considerations you have to have with this, again, going back to the limited supply and hot demand, is make sure you have clear communication. Your user experience will go a long way as to keeping people as a happy customer, as a return customer. You want that, so clear communication. That means if something bad happens, oh no, the payment processor didn't work, oh no, I couldn't get this ticket. As long as it's clear, go for it. Make it fair for your users. Make sure that there's not a big delay to the point that it inconveniences your users. You want to keep your users happy. Again, you don't want them waiting much. So if you have to do something like retries and timeouts, make sure it's a reasonable amount of time. And keep in mind that you want it so that it gracefully degrades if you can, because again, gracefully means you're using messages that are clear to your users as to, hey, we're experiencing some high loads, please be patient with us, or please try again later. So that's the situation of You have an online shopping cart. You have a hot sale. It is in demand. Now let's talk about another situation. Let's talk about the social media feed freeze. I'm not talking about any platforms in particular, but picture this. So you're on a social media platform, and they have geographical regions, and all of a sudden, one of the geographical regions drops connection to the main data center. What does that user experience look like? Well, for those of us who are still connected, we might not have issues, but what's that look like to the user that's disconnected now? Users in the disconnected regions could probably still work with local users depending on how it's configured. But that disconnect, what's it look like? As a disconnected user now, am I looking at a blank screen? We don't want that. Maybe they're getting outdated feeds now, missing the new posts from their friends in the other regions. They're seeing likes and comments that are like the numbers aren't lining up. Why is that? Because they're disconnected. This is problems with partition tolerance and eventual consistency. Eventual consistency is one of those that takes a bit to get used to, and we'll talk about how to handle eventual consistency here in a little bit. But the goal is you want to, again, maintain your usability. You want a usable system, especially system disruptions, communication issues, communication being networking issues, better UX with data replication. So as I save stuff, is it going to work well? Are other people going to see it in a timely fashion? We don't know. So if you're in a situation like this, where you have a geographic region just go down, something to consider. Consider asynchronous writes. So these are write operations that are acknowledged and then added to a queue for processing. From a user experience point of view, the acknowledgement is, yes, this has been taken care of. We'll write eventually, and by eventually it's, okay, now we're reconnected, now let's push it to the queue where we can process it. But the thing is, you need to make sure you're working with reliable queues and other mechanisms for processing with an eventual consistency. So when I say eventual, I'm not talking about like, oh, eventually down the line somewhere unknown completely. It's more eventual in terms of your data consistency. And when I talk about eventual consistency, I'm not talking about I save something in the database and that's immediately available. That's not eventual. Eventual is I save something to the database. It might be immediately available. It might be available in a couple seconds, or whatever the time is that is comfortable for your users and their situation. So asynchronous writes is an option. Fallback mechanisms. So you're going to see fallback mechanisms in a couple other slides as well, because it makes sense for those scenarios. Basically, if you're trying to deal with an operation that is not responding or is disconnected or is overloaded, you might need to fall back to an option, another alternative option. For example, so in our scenario here, you could say, all right, I'm hitting the primary data center. Is my primary working fine? Cool. If not, okay, how do I do fallback? And so when we talk about fallback, it's going to be, you could have options, or you may just have a single, this is how we fall back. Now, the problem with single point of fallback is that what happens if your fallback fails. So you need to consider that as well. Health checks. Health checks is another practice that we recommend when dealing with distributed systems, because those health checks help you to understand whether particular parts of the system are responding well or not. Are they healthy or are they unhealthy? And then if they're unhealthy, what do we do? Do we fall back onto something else? Is it one of those that we can gauge and then retry? Is it a timeout? What do we do? So health checks, what's nice about them is that it gives you the ability to see, wait a minute, there's failure coming up ahead, and now you can go, okay, not healthy, what do we want to do? Log, notify admins, maybe there's meaningful alerts. We've got a slide on meaningful alerts here coming up. But health checks are great in terms of both for orchestration and understanding whether they can route traffic to those servers, as well as, okay, I need to call this API, and this API is actually not healthy right now, so I need to go to plan B. Another option is the circuit breaker pattern. Now this one here, we don't have the diagram. We have the diagram for it in a future slide, because circuit breaker also applies to multiple situations. And circuit breaker allows you to prevent calls from a failing service. Like, you'll make the calls, but then you'll eventually just stop. Why? Because you've triggered the circuit. And so we'll look at that in another example, but just know that being able to stop calling to that failed service means now you can tell the user, we can't access the service, please try again later. Or make a plan B, and how do you want to handle their details. Client-side caching is also an option. So you could use a cache data feed. You could use local caching. You could use service cache. But think of it as having a cache means that your users could at least see the outdated social media feed. They're not looking at a blank screen of just things loading. Or they're not looking at a screen with a fail whale. For those of us who've been around long enough, you'll remember what happens when the server can't connect. That was what we would see. Client-side caching, though, makes it easy because you're getting that user experience. It's consistent to what they would see with non-stale data as well. I say non-stale data. I mean, your cache could be actually fairly fresh. That's something you have to keep an eye out for, is invalidating the cache and updating the cache. So what does client-side caching look like? Well, I hit to the point where I'm like, I can't get out. My social media feed is looking like it's not updating. Well, let's see if there's anything cached. Can we show that? Otherwise, is the network on? Yes? Oh, sweet. Otherwise, you have to deal with the stale cache. So that's how the caching part works. All right, let's talk about local read-write options as well. So you might have the ability, depending on your configuration, to write to a local replica. If that's the case, with the local replica, you're going to end up writing locally, and then your replica is part of a cluster, and that cluster will have ways for doing the synchronization. You shouldn't have to write the code to tell it to synchronize. Usually that's handled outside of it, but just so you're aware, if you happen to be some of the people who write the code that do all this synchronization manually, thank you. But you can see here, if you're in a clustered environment and have a local replica available, then you can do some reading and writing there as well. All right, I did mention we're going to talk about eventual consistency, because eventual consistency is one of those that, for those who are inexperienced with the asynchronous world, are just like, wait a minute, what do you mean my data is not available right away? We learn to find those tolerances in distributed systems of what can our stakeholders, what can our users handle in terms of delay in data. Eventual consistency means your changes aren't going to be available right away. So these are some of the strategies we talk about. We talk about things like read repair. So you might get potentially stale data. If you get potentially stale data, then it will update the replica with the latest data. You'll hear something called anti-entropy, and we're going to see a flowchart on the next slide where you're going to see these terms in action. So anti-entropy is the background processes will compare data across the replicas and do the reconciliation. Again, this is code that's already taken care of for us. It's done usually at the server level in the server stuff. So if you are the people who do this, thank you for writing the code for us so that we don't have to do it. Because otherwise, what you think is distributed systems and complex already, under the covers, is worse. It's more complex. So yeah, anti-entropy, again, is background. Last write wins, so this is where we get into conflicts. We have multiple people trying to access a record, and the update with the latest timestamp is the final version. You gotta be careful with this because of user experience. User experience can be pretty difficult. And then the last one are vector clocks and Lamport timestamps. And this is used for doing the order of events in a distributed system more than just simple timestamps. And this is what the flow looks like that I was talking about. So what happens is you write to the replica. There's a replication queue. And then this is where the replica is working with a cluster. So that means there are other replicas and they have this logic, but this is the logic they go through. So you can see, is there a conflict? No, okay, we'll merge it. Otherwise, how do we resolve our conflicts? Last write wins. There's fairly simple vector clocks and Lamport timestamps are a little more detailed, a little more fine-grained. Here's the anti-entropy and read repair, so you can see where they all fit. All right, so some user experience considerations in this case. Be clear with the users if they're in a degraded state. So if they're in a spot where they can get stale data, you might want to have some kind of wording there. Let them know that, hey, it's limited connectivity. And this is whether it is server related, so the server is down, or it's client side related. Make sure that the limited connectivity is clearly explicitly stated. Again, if they can write locally and then have that synced later, that helps. Background synchronization is nice because then you're not interrupting the user. And then with conflict resolution, make sure you have a clear strategy for this. This is going to depend on, honestly, it might depend on even the scenario. So you might have your general, if we have two people who want access to this particular cup of tea, and we only have one cup of tea, how do we handle that conflict resolution? Have that conversation with your team, because it makes a little more sense when you talk through it. Okay. So, questions so far? If you have any questions, again, please feel free to post in chat. I am watching the chat. We do run a subscribers only chat to limit the spam. So, all right, the next distributed system setup I want to mention is the movie streaming microservice Meltdown. Before I bring up the slide, I want to make sure I'm clear. I know there are people out there like, oh no, not AI generated images. I did this on purpose to avoid copyright violations. So, yes, we're talking about a movie service. And the online movie streaming service is got microservices under the covers, and there's a recommendation service, but the recommendation service is having a bad day. And so it's got a sudden surge in traffic and starts to fail. The movie detail service directly depended on our recommendation service, then that would be impacted as well by the recommendation service's degraded operations. Well, if the movie detail service is now impacted, this is going to be a bad situation. You don't want that. You want things like circuit breakers. You want things like timeouts. You want things that can separate them, honestly. So we'll take a look at that. So users trying to view this information might encounter errors and timeouts, and the user experience is usually not that great. These are problems with cascading failures and resilience. This is also a problem usually with the architecture and the way it was built. Because you want to have, like with microservices, you want them independent. You don't want them dependent on each other. So again, preventing cascading failures, enhancing our resilience, and maintaining that system stability. So here's our circuit breaker that I was mentioning earlier. I told you it would be back. So with our circuit breaker, we have normal traffic hitting, which is fine. And then we're hitting our recommendation service, and it fails, so then we need to close the circuit. Now, what does that mean for us in the grand scheme of things? That means that when I hit a certain amount of failures, so you configure that, and I have code to show you the circuit breaker in C# with poly here at the end. But this is, you set the failure rates to trigger that circuit breaker, and then have some kind of fallback, or some other way to say, hey, this is a problem we have. And again, it requires the library to manage circuit states, thresholds, and fallback. You don't have to do it from scratch, though. There are things like poly. And so I'll show you how we do that with poly. Timeout is another pattern you may see in this case, where the microservice is failing. You might want to set timeouts to prevent waiting forever. So you're going to be like, okay, this microservice, this service that I'm hitting, I know usually takes about 500 microseconds. Why? That's what it does. Okay, fine. We'll set our timeout to that. So you set your timeout to a time that is expected based on the latency of the service. And you want a timeout that makes sense for your user. In the case of our movie recommendations, so as the client, I'm like, okay, give me this movie page. It hits the gateway. The recommendation service is just like, I don't know what I'm doing here. I'm not going to give you any recommendations. I'm kind of busy. I'm overloaded. So there's a delayed response. When you set the timeout, it hits that timeout, then you get some kind of way of handling that. Bulkhead is another pattern that we'll see with distributed systems. This is where you allow your resources to be segregated so that only the services that need them are using them. You pay close attention to how your system and your services are using those resources so you can allocate them separately. The term bulkhead comes from boats and the way that they're built. How if you hit one part, it shouldn't impact the entire ship. It should only be contained. Similar deal here. So let's say we have UI and author in one pool, and our recommendation engine is in another pool. Are UI and author happy? All those services do not rely on the recommendations directly. So those are fine. But recommendations is having issues, and it's overloaded. So bulkhead, when you separate them like that, then you make it easy so that you're only impacting a small section. Fallback mechanisms, again, comes back. So again, if our movie recommendation just not cooperating with us, you'll see here a service healthy. So that's, again, health checks. Health checks are good, so you can check to see, is this really a healthy service? It is? Okay, then make the call to the recommender. Oh no, the service isn't healthy? Okay, now we gotta fall back. This return popular movies or last known data, that could very well be cache data as well. But it doesn't have to be cache data, it could be default data as well. So if you have default values, or default behavior, or default screen that you would show, then that's also an option. And you want to make sure that you give your users the ability to see an alternative without misleading them. Okay, let's talk about idempotent operations. Idempotent is one of those that I was talking with somebody recently, and they're like, that's one of those words I can never remember what it means. And the thing I remind them is that there's a retry. Let's say you have an action and you retry it, then it should only happen, it should happen once, and then it should let you know, hey, this has already happened. You don't want to, so the example I like to use is you don't want to use the payment service multiple times. And now you're charging a user for 3, 4, 5 times their order. That's expensive. That's a very costly operation thing that you don't want to do. So that's where idempotency makes a huge difference. Now, when you're doing idempotent operations, so when I call and do something, I should get that same effect each time. Now, this one here is fairly tame because it is just a get. So it's just give me data. Recommendation service, keep in mind, is overloaded and says nope. So let's retry that, and then we get the response. Gets are fairly easier to make idempotent if it's just a straight get. It's when you start writing data and updating data that the idempotency becomes a little more challenging. And it's one of those where you usually have a transaction ID, for example, and then you check to see was that transaction completed successfully. Idempotent operations are also more resilient to transient failures. So let's say I try to make a update and I lose connection in the middle. If I rerun the idempotent thing, it should update. It should not be causing issues and saying, oh, you placed that order again, and you placed another order for the same things again. That wouldn't be idempotent. If I placed an order and it got caught in the process, it would still only place that order once. The key here is no unintended side effects on retries, because our retries are going to happen. But again, this is careful API design to make sure that your transactions are idempotent. Health checks again. So thinking for orchestration platforms and load balancers, they use it to see can traffic be routed. This is, can I call the service and reliably get the results back? Think about critical dependencies. This service, like I used to work in e-commerce, and one of the APIs we had to call was to a credit card company because we had our own store card. And so people would apply for the card, and we would want to make sure that they can do the application without having multiple credit hits, because again, that has its own implications. So making sure, okay, is that service healthy? It is healthy? Okay, we can use it. Let's go forward. All right, let's talk about message queues. So communicating via message queues, async. That movie recommendation that's down, wow. These are a reliable message broker and careful design of formats. You can see here with our message queues, again, this is async. So you can acknowledge to the user, hey, we see that you did this action. You can tell them to please wait. Or you can just run it through and notify them as it goes through the steps. So asynchronous notification will come up on another situation as well, just so you're aware. When you're dealing with asynchronous updates, keeping your user informed can be a challenge. So asynchronous notifications help. Sagas will help with that as well. We'll look at those here too. All right, another distributed system setup that you might see deals with payment processing. Payment processing happens on a lot of different projects, not just e-commerce. Think about hospital bills, think about taxes, things that we don't really want to think about, but it's all payment processing under the covers. So the problems we run into in that kind of situation are, again, the idempotency, the consequences for not getting things right, as well as message delivery. So an online payment gateway will talk with the bank's API to say, hey, let's process this transaction. And the network issues, there could be network issues locally, it could be at the server. Either way, you just need to make sure that that transaction is idempotent. So let me be able to retry this safely and without side effects. I don't want duplicate payments. That would be bad. So our goal is, again, preventing users from the incorrect charges. Let's do this now, rather than they pay for the orders multiple times. If we could avoid issuing refunds, even better. But better user experiences during payment processing. And how do we handle these failures, especially with payment processing, when, again, transient issues happen? So here's our idempotent operations, again with the idempotent, but this time we're talking about a post. So how do we do that? Because a get is fairly safe. Give me this object, here's my request object, it'll give me something back. But if I'm posting, when I post to something, you have to hope that it doesn't post multiple times or that it's idempotent. So this is what we do. We take the same payment request should yield consistent results. So have an ID. In this case here, the example has you're posting to an endpoint, you're making a charge with a transaction ID of 123. So the API is like, okay, I don't see this. But then you're going to retry that post, because retry is an option in distributed systems. It's one of the ways we can resubmit things. The bank API is like, okay, that's been processed once. How does it do it? It's because of this ID here. You have the ID with the request and check to see if that ID has been processed. And you want this so that you can prevent duplicate charges. Because payment processing is costly when it comes to failures and not getting idempotency right. Now, another solution you could deal with is exactly once messaging. Asterisk, and that exactly once is pretty difficult and complex to get. You have to make sure that all the planets are aligned. You have to make sure that everything makes sense in the scenario. It's almost like perfection. It's kind of hard to get. So the other thing we recommend is at least once with idempotency. So exactly once versus at least once. So ensuring that the message is delivered and processed exactly once, that's exactly once. But again, it can be difficult, it can be complex. At least once delivery makes a little more sense. And this is what it looks like. So we have submit the payment, deliver the message. API is like, yes, we got it. Okay. But if there's no after a certain amount of time, then we have it sent again. Now, notice it says it requires an idempotent handler, so you just need to make sure that the code is idempotent in that case. Payment processing logic will handle the duplicate deliveries, so it should be able to, again, check and see, hey, have we had this request here? Hey, look, that request ID, we've already had it, we've already processed it, here's the response. So that's what happens with that. Again, goes back to having an ID, a correlation ID, a request ID, something to track what's going on, whether that transaction is processed completely. If it's not complete, have a state machine. Use the state machine to track where things are. So the different statuses, for example. And so you can check and see, where are my funds? What are their statuses? State machines, again, give you tracking of the status, and watch out for the out-of-order events. All right, let's talk about sagas. So sagas allow you to track payment processing, for example, across multiple services. And where are we in the process? Maybe you've got an order that goes to payment authorization and inventory update, and you're like, all right, where are we in the process? And where is the payment processing in this process? What does it need? Does it have everything to go forward? So you can do notifications to the user on phases, which is good because then they don't have to be wondering where they're at in the process with those notifications. But you still have to consider things like compensation transactions for rollback. This is what I mean by compensation. So let's say that you're dealing with a payment and we're going to take money from the customer. Is that good? Sure. All right, well then the merchant gets the money. Is that good? No? Okay, now we have to undo it. Hold up. What happens when we undo it? So now we have to have a compensation process, a compensating transaction. So you have to consider rollbacks at points of failure. But with sagas, what's nice is as a customer in this case, I could see that they took the money from me. And then I could see that the merchant has the money. Or I can get the notification of, no, this wasn't successful, so now I need to retry my payment. We'll have an upcoming webinar here in July where we're going to talk about implementing sagas amongst other patterns. A reconciliation process is another approach when you're dealing with payment processing. So if you're concerned that your payment processing is out of line accounting-wise, maybe you did do multiple charges that you shouldn't have, you can do reconciliation processes. I used to see these when I was working in the financial industry. These were jobs that usually ran overnight so that the next morning they could deal with the clients. But it's one of those where you get the daily gateway logs, you get the bank statements, and then the reconciliation service checks to see, so the transactions here appear on this other one. Is there a mismatch? If there's a mismatch, we need to raise the alert. But if they match, it's all clear. This was good for catching billing errors. It was good for us to capture potential fraud. Clear error messages. This is important in terms of user experience. So when you're dealing with something, in this case, again, the example is payment processing, but it applies to everywhere. Be clear. Don't say something went wrong. An error has occurred. How many times have you seen that and you're just like, okay, an error has occurred. Now what do I gotta do? I gotta go to Event Viewer. Now I gotta figure out which one of these is the actual error. Don't do that. Don't do that. Make the process less vague, because honestly, as users, the last thing we want to do is get that frustrated with the app that we just close it, walk away, and then we're miserable and grumpy the rest of the day because that application just wasn't helpful and it just set me back more. You don't want that. You want happy users. You want users who like to use your application. Because if you have that, you'll understand why I rave about users. You take care of them, it's a beautiful thing. Make the process less vague. Don't be like this doctor. Well, you're sick. Thanks, I know I'm sick, but what am I sick from? Give details. Give details that your users can understand. How can they be helpful? Is it something that they can retry? Is it something where, you know what, our servers are down for maintenance? We have a maintenance window from 1 a.m. to 4 a.m. The servers will be unavailable. Now you're setting the expectations with the users of these times, the service is not available. Come back later. So be explicit when you can, because your users, they just want to use a system. If they don't understand what the problems are, that's frustrations. That's a rough user experience. If it's a payment method issue, when you call to make a credit card payment in an API, you do get reasons sometimes of why it got rejected. Take advantage of those messages when you do get them and display it for your users to understand how they can help it. And also map your back end to user-friendly front-end messaging. You know those custom exceptions we like to use? So it's clear in our logs when we're like, oh, what's this problem? Oh, look, there's a custom exception. Give our users a user-friendly error message that maps to those custom exceptions. All right, there's asynchronous notification. I mentioned it would come back. And so with the asynchronous notifications, making sure that, hey, everything is working fine. Sometimes it's not a synchronous process, so notify them later. Send a text message, send an email. Before you do those, make sure you have their permission to do so, because there are guidances behind it, but make sure you notify them somehow. Even if it's, you know what, I'm going to notify them in my shopping cart that, hey, by the way, your processes or your order is being processed and it's at this state. But again, reduce the anxiety and be clear with your clients. And using reliable notification services helps too. Retrying with backoff is, again, another thing. It's exponential backoff. There are tools out there that make it easy for you. Again, have I mentioned Poly? I really like Poly for some of these patterns. But retry with backoff means that I'm going to call to the API, and that's not going to work well, so I'm going to have to wait, and then retry my call. I'll wait a second, no work, 2 seconds, no, 4 seconds, and then continue exponentially up. Now, at that point, with retry with backoff, you'll have an exponential backoff, but you'll still probably have a point where you'll be like, you know what? The API is just down, and I can't move forward here. And then, so you have a limit on that as well. All right, configuration chaos. This is our second last scenario. Again, sometimes configuration in a distributed environment could be a challenge, but distributed configuration management doesn't have to be difficult. If you think about a large application like microservices that have various configuration settings, so database URLs, API keys, feature flags, things like that. Each service might have its own configuration file, and now you got to go manage each service. Don't do that. Get it into a centralized area for your configurations. Now, that said, you're like, well, what can I use? Well, there's like Spring Cloud, there are different configuration managers out there, but make sure that you do it in a centralized spot rather than having to juggle each service manually, because really, who wants to do that? And this gets chaotic when you have it across different servers and across different environments. Now your details have gotten a little more complex, because now you have to go, okay, I have this feature and it's enabled in dev and it's enabled in our QA environment, so our QA team can test it, but we don't have it enabled in production because testing hasn't finished yet. Did we even put the feature flag out there in production? You see where this goes. The configuration chaos, you want to be consistent. Consistency is key. Let's make it easy to update. Now, at this point, you might be like, oh, it's configuration, that's IT, that's not developers. Hold up, developers are IT, first of all. But second of all, this kind of stuff's important to know. Because if we can make the people who manage our infrastructure and who manage where these things get stored sometimes, if you make it easy for them, again, you'll understand why I get happy working with everybody. Because you work together. With centralized configuration servers, so think of it as you have a configuration management server, and all of your services will get their configuration from the server. This allows for more stable and consistent application behavior, which is good. You may have heard me mention feature flags, because you can roll them out, you can roll them back. You do it at the central server, it gets sent out, or maybe they're subscribing and they pull it, and so then it's done. The key with this is you need to have a reliable central server, and if you have a singular server, so you're not working with a clustered environment or a scalable environment, understand how this works with a single point of failure. So what happens if your config server goes down? Is everything down? Distributed key value stores, another solution for configuration management. So having something like etcd, and notice it's got a cluster. And so the services go to the cluster. Cluster is going to have the store spread out across the nodes. Again, similar to the centralized configuration server, the difference in this case is that it's not one single server, it is a cluster. And with this, you need to make sure that something is integrated with that cluster to read and watch for changes. Some systems will do a pull, some will do a push, some support both. What do you implement? It depends on your situation. Push-based configuration updates are a thing. And so you could have your changes on a config server, and that config server then pushes to the services that are registered to listen to it. So then service A and service B are listening to the config server. Config server is like, I have an update. And service A is like, got it. Service B is got it. Those are your acts, your acknowledges. So again, having a centralized server or centralized cluster to manage your configuration makes it easier to just roll those changes out from there. The trick you gotta watch with having configuration servers is making sure that they're polling or getting pushed to consistently in a timely manner, and that they can update safely. Yeah, it's kind of important to update safely, because if it updates catastrophically, you need to have a plan to roll back. All right, watchers and listeners is another thing to consider in our configuration chaos. And so watchers and listeners are there specifically to listen to the config store. There's a change watcher, so it's watching to see, did anything in that config store change? If so, I need to talk to the services that are using this watcher to say, hey, by the way, we have config changes. And service A and service B are like, we got you, watcher, thank you. That's watchers and listeners. Watchers are the ones who are watching the config store for changes and responding accordingly. Configuration versioning. This is important because if you have a configuration that you push out and now it's breaking things, we have breaking changes, intended or otherwise, because sometimes we have accidental breaking changes that you're like, oh, I didn't even see this one coming. You want to make sure with your configuration versioning that you can go, okay, I'm on this version and it's stable, we're good. I'm going to the next minor revision, we're good. And then the next one, and now all of a sudden this stops working. Well, what happened? So when they show on here problem detected, yes and no, you could do a, yeah, we'll roll back, or no, let's just continue on, which is good. But do you have to roll back? I want to talk about a process I saw last night. Talk about timing. So I have a website that's PHP based. Yes, I use other languages besides C#. And it was running PHP 8.2. And the web host is like, hey, we have PHP 8.4 available. PHP 8.3 is their stable, but 8.4 is newer, and so it's available. And I'm like, okay. And so I was like, you know what, just go out to 8.4. And they're like, are you sure you want to go to 8.4? Yes, I'm sure. Okay, what do you want to do if this fails? So they have processes behind the scenes that will test to see if it works with the setup. And if the test fails, do you want to go forward with it and solve it on your own, or do you want to do a rollback? That kind of process, it's helpful for users who know what they're getting themselves into. So your problem detected could be a yes rollback, or it could be a yes offer to your users. Do they want to deal with the debugging themselves? Are they advanced users? Or is it one where they need more guidance, and so rollback? Mutable configuration is another one. So your config is immutable during the runtime. If you want a new machine with a new configuration, you spin up a new machine and roll it out. Think of it with like blue-green deployments or canary deployments. And profiles for environments. So different configurations, different environments. So you have different databases for your different environments, different connection strings, and feature flag toggles, things like that. So this helps with configuration chaos because you kind of wrangle your chaos into their environment-specific files. In this case, YAML, or think of like appsettings.json. Okay. The last one's Logistical Labyrinth. We are running short on time, so I'm going to speed up a little bit. But rest assured, there are going to be blog posts on the NimblePros blog, as well as videos on the NimblePros YouTube, because we're going to have fun with these, as well as do the code samples as well. So Logistical Labyrinth goes into what happens with debugging. Debugging in the distributed environment is a challenge. Distributed tracing and monitoring makes a world of difference. And so let's make it more manageable, and let's track down a request across multiple services easier. When you're looking at logs, looking at IDs helps. Understanding what those IDs represent helps. You want a unique ID for a request? Each of those services are going to record their interactions for that request. That could lead to faster debugging times. There's libraries Jaeger and Zipkin, so you could use those for your tracing with the distributed tracing. So this is the example I like to show. where we have the user makes an order. That ID for that transaction, that is not necessarily an order ID, it's a transaction ID of some sort. It gets passed on. You see it in all these different calls. You may see it as an ID. You may see it as a correlation ID. So the correlation ID points back to the ID of the initial transaction where it started. So distributing tracing, you still pass that ID along. You can do centralized logging. So centralized logging allows you to say all these different services, bring your logs into one central spot. So there's Elk Stack, which is Elasticsearch Logs-Kibana. There's Grafana. We have a webinar on Grafana. I will have a link here, actually. Post that in chat. So that is this one. But basically, centralized logging. Get it all in one spot. Now, why would you want to do that? Because do you really want to go on the different services and look at their logs individually and then try to do that correlation on your own? Or think of like SQL tables and joins. If it's in one spot, a lot easier. Again, request IDs and correlation IDs. The request ID is point of origination. The correlation ID is going back to, okay, this goes to this request ID. So that's where your correlation IDs tie. But again, going back to that central logging spot makes a world of difference rather than trying to do all those joins manually. Meaningful alerts are crucial. You want alerts not for the sake of alerts. My friend Leon did the talk about how alerts don't suck, but your alerts suck. You want alerts that make sense for what you're going to deal with and that you're actually going to address. So here you can see there's an alert rules engine of, okay, are these conditions met? Oh, they are? Okay, now we need to send an alert. Oh, we've had these payment failures, more than 5 in a minute. We probably should look at that service. Comprehensive metrics are another thing that could help when you're trying to debug in a distributed environment. Again, getting all the metrics into a dashboard. And this is where we talk about Datadog or Grafana or Prometheus. The webinar does a good job of showing all those. All right, so those are the different scenarios in distributed environments and ways we can tackle things with the different design patterns and practices. Let's talk about some libraries real quick. So there's Poly, which is at vnext Poly. Notice this is C#. So this is a circuit breaker. We're going to have some videos come out about eShop on web and using some of these patterns, so stay tuned for that. Ardalis guard clauses, again, catching failures and taking them out when you don't need them there. Ardalis result, again, allowing us to be more clear as to, okay, this is the type of result that we're getting back. Now we can be more explicit with what we're dealing with. Mediator, again, so you're not executing multiple times. Will help with that. And then fluent validation is making sure you're validating your user input. Very important for when you're dealing it distributed or otherwise. Now, if you have any other questions about distributed systems and design patterns and practices, feel free to let me know. Drop me a message, sarah.dukevich@nimblpros.com. We do have some upcoming webinars. So in May, we're going to talk about authorization, authentication. We'll talk about OAuth 2.0 and OAuth 2.1. In June, we're going to talk about domain events and what are domain events and how do you handle them using C#. And in July, we're going to talk about in-service bus. If you enjoy these webinars, you can find more at nimblpros.com/on-demand-learning. All of these are made available there. We have NimblePros Academy. We've just launched the ASP.NET Identity in Action course. It is no longer in early access. We also have those bundled as well. The design patterns you saw today will also have design patterns courses going there very soon. So stay tuned. And if there's anything else you need, feel free to reach out, whether it's somebody to help facilitate event storming sessions or teach your devs about DDD, CI/CD, clean architecture, any of those, event storming, authentication, authorization, reach out to us. We'd love to work with you. All right. Thank you so much for coming. We'll see you soon.